Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about the geometry of blow-ups. The blow-up is one of the most fundamental morphisms in algebraic geometry, and that's because it's the most fundamental example of a birational map which is not an isomorphism. So it's very close to being an isomorphism, but it's not an isomorphism. Okay, so let me tell you what it is, and the setup I want to pick here is I'm going to look in the projective case. You can also do this in the affine case with a very simple modification of what I'm going to do here, but suppose you have projective space P of V star, so V is just some vector space over our algebraically closed field, and then we have X is some projective variety sitting inside that, and then we're going to have L is some linear subvariety of this which sits inside X and is not the whole of X. Okay, so we're going to just look at blow-ups of X along this L. Okay, so in the case of a linear subvariety, so that's a special case which is interesting enough as it is. Okay, so since this is a linear subvariety, okay, it corresponds to some W, which is a subspace of the global sections of O1 on this projective space. And this O1 is just V. So you've got W is some subspace of V. That's the space of all the linear forms which carves out this linear subvariety. Okay, and remember we have this projection map. Okay, so of course if you have W is a subspace of V, then you have a linear map from V star to W star. That's like a quotient map. So you have certainly a map of affine spaces from V star to W star, and you can try to projectivize that. The only problem is that all the things that correspond to L, okay, inside P of V star, they would go to 0 inside W star. So that's the base locus. So we have this projection pi L from P of V star minus L to P of W star. And remember, the other way to think about this P of W star that's adapted to this situation is as follows. Okay, so the way you want to think of this is it's the set of all linear subvarieties of P of V star. It's the set of all these L tilde linear subvarieties of P of V star which contain L and is one dimension bigger than L. So dimension of L tilde is dimension of L plus 1. I'll do a little example if that's not quite so clear to you. I'll do it when we really need it, okay? So what are we going to do with this setup? So the first thing we're going to do is we're going to look at the graph of essentially this map when we restrict it to X, okay? So the graph, we'll call it gamma, is going to be mapped from X minus this L, because it's not defined on L, and it maps to the product, firstly X, is the first factor, and the second factor is the image of this P of W star. So what happens is you take a little X that's inside here, and it's a graph, so the first element inside here is just X, and then you just apply a pi of L. We've removed the L here, so we can apply pi of L, so you land in P of W star, so pi L of X. And that's of course the graph of this map. Okay, so of course it's a graph. You can also do the inverse of this. You can just project onto the first factor, okay? At least if the first factor is inside X minus L, you can project onto the first factor, and that's going to be an inverse to that. Okay. So what's the definition of the blob? We can now define the blob. The blob of X along L, what we're going to do is we're going to look inside here, okay, X cross P of W star, and we're going to look at the image of this, okay, which is going to sit above X minus L, and we're just going to close it up, and that closure is called the blow up of X along L, and it's denoted by this BL subscript LX. Okay, so that's what it is. And one thing that's rather interesting is that up to isomorphism, it's independent of the embedding of X inside this P of V star. Okay, so that's the definition that I have here. You can also do this for linear subvarieties of affine space and affine varieties. Okay, you just use a projection map in that setting. Okay, but this one is a little bit more interesting. Okay, so there's quite a bit there, and maybe you're not too sure about what it should look like. So let's go through a little example, which hopefully will clarify how things work. Okay, so the example here, I'm going to sit inside what's my P of V star. That's just P2 in the variables X, Y, Z, and my X is just going to be the nodal cubic curve. Okay. So it's going to be given by this cubic equation, y squared z equals x cubed minus x squared z. And hopefully you know it's a nodal cubic in the sense that it looks like this. So there's this singularity, there's this node here at the point 0, 0, 1. Okay, so I'm going to call that L, and that's the point that I want to blow up. I want to blow up this nodal cubic at this nodal point here. Okay, so what do we need here? So firstly, we need to look at this graph map. So we're looking at x cross P of W star. Okay, so x is this blue curve here, this blue nodal cubic curve. And what's P of W star here? So what's W star? W corresponds to the subspace of the span of x, y, z. That's corresponding dual to this point L. So that's just the space spanned by the x and y, because x and y, they generate a basis, or they are a basis for the linear functions which are 0 here. Okay, so that's generated by x and y. So that's a two-dimensional space. So P of W star is a P1. But remember what I said here, the way I want to think about this is as follows. I want to think of this as a set of linear varieties inside P2. And which linear varieties do I have? They're the ones which contain this L, so they contain this point, and is one dimension bigger. So that means here, this is 0-dimensional, this L. So I want one-dimensional things which are just lines which go through this point. So it's this P1 of lines that go through that point. That's my P of W star. Okay, so let's have a look at an example of how this graph map works. So let's pick a point Q inside here, which is not on this L. Okay, so let's see where it goes to. So firstly, we're going to cross this here, this X here, with P of W star, which is this P1 of lines going through here. So this P1 of lines, I'm going to write it as this purple thing is going to be like this. That's my P of W star, that's a P1. Okay, so what happens to this point? Where does it go? So firstly, the point Q, in the first coordinate, it gets sent to just Q. Okay, so it's over like this. And then we're going to cross it. Here's my P1, okay, my PW star. So where do I put it along here? So it's going to sit at this level, but where do I put it along here? Okay, well, it corresponds to the image under this projection, which is just, of course, just the line which contains both this L and that Q. That's how the projection works, okay? So it's just that one there. Okay, so that's Q comma pi L of Q. So you do that for every point that's not L, and you trace that out, okay? So they're the ones which don't sit at that L, okay? And then what you do is you're going to be missing 2 points, and then you close it up. So what are the points that are missing, okay? So this is the key point, okay? So basically you're missing what's above this here, okay, L. Okay, you want to close it up. So let's see what happens when you close it up. The easiest way to think about this is to look in the case where the field is the complex numbers, and we can use Euclidean topology, and just take the limit as this Q goes towards this point L. And when you think of it this way, there are kind of 2 ways you can do it. You can come across like that, and that will give you this one here. If you come across like that, this will come towards the tangent that goes in that direction. And so the point is that when you get to there, okay, you'll have this line which corresponds to a point in P1. So it would be something like this point here. Okay. On the other hand, if you approach it from the other direction, if you take this Q and you move the limit till here, then that's fine. You'll get towards, in this X factor, you'll go towards L. But in this PW star, where are you heading towards? You're heading towards this line here. So that's this one here. So you see what's happened is that in this blow-up, when you close it up, okay, because you can approach it from this kind of 2 different directions, so this cubic, nodal cubic kind of has 2 branches locally here. Those 2 branches get separated when you do the blow-up into these 2 points. Okay, so the black tangent line here will correspond to this one here in the blow-up, and this orange tangent line, when you go along this way, will correspond to this one here. So here we see something that's rather interesting, right? Okay, so what's happened to this noble curve when you blow it up is that we've desingularized it. Here there was a singularity, but now it turns out that it will actually be smooth, okay? So that's something that's rather nice about the blow-up, and tells you one reason why it might be an interesting thing. Okay, so let's do another example. So rather than looking at X as being some proper subvariety of this P2, let's look at the whole of P2 and do the same thing. Okay, so if we do the whole of P2 and look at the same thing, so what happens is that we look at the graph of this map. X here now is replaced with P2, P2 minus L, P2 minus this point. So away from this point, okay, you'll just have P2. So you have all of P2. But what happens at this point here? How can you approach this point? You can approach it from every direction. So you have all possible elements of PW star in there. So what happens is that if you want to blow up P2 at this point, you'll get something that looks just like P2 everywhere away from L. But what's happened to L? The L is now replaced by this whole P1. So that's pretty interesting, okay? That what's happened here is that it's replaced it with a P1, but I haven't just taken this plane and stuck a P1 through it. I've made it in such a way that actually it turns out that this blob will still be smooth. And that makes it really, really interesting. Okay, so one of the things that you've noticed is that, well, the actual X that you start off and its blow up, they look very similar, okay? And this is the key reason, as I said earlier, why the blow up is such an interesting and important concept in algebraic geometry. So the key point is that this blow up is going to be give you something that's birational to the original. Okay, so let's go through slowly what's happening here. So suppose you have the blow up of X along some L. Okay, we can always look at this as inside, because it's the closure of graph, it's inside X cross P of W star, and hence you can project onto X here. Okay, so you start with X, you blow it up at L, along L, and then you can project this down onto X. Okay, so that gives you a map from here to here, and it's clearly an algebraic map. Okay, so it's clearly a regular map here. And the key point is that, well, essentially, what was this? So if you go back up the other way, what was this blow up? Essentially, you look at X minus L, and you look at the graph map, so you map it essentially by the inverse here, and the closure is this blow up. So that means that that's the inverse. The graph is the inverse to this map as a rational map. It's not defined everywhere, so it's only a rational map. Okay, so this is this projection map is actually birational, and that rational inverse is given by the graph, and that's rather neat. So the other thing that's rather interesting is to look at what's happened where the change occurs, and the change occurs over L. And so usually what we do is we look at the inverse image of L, and if we have X equals P of V star, okay, what you will find is that that, like in this sort of situation here, this inverse image of this L is going to be a P of W star bundle over L. I don't want to go over that too much, but in this particular case here, you see when you start with this point L, we blew it up at that point, okay, with this P of W star, or you get all of, you can always approach every direction, so you get all of P of W star lying over that point. And in general, if L is not just a point, but it's whole linear subvariety, you'll always get that P of W star over every single point there. Okay, and that's called the exceptional divisor. So usually, that's what you call it. Okay, the inverse image of that L is the exceptional divisor. Okay, so now what I want to do is I want to specialize to the case of surfaces, because it turns out that if you try to blow up a point on a smooth curve, you don't get anything new. It's only when you look at singular curves that it does something interesting. But when you have smooth surfaces, as you can see with this P2, even with a smooth surface, it will do something interesting, and there's a lot of interesting geometry that's associated with it. So let's suppose now we start with X is some smooth surface, and little x is a point on it, and we're going to look at the blow up of X at this single point. So it's only a linear subvariety of any ambient projective space it sits in, and I'll call it X tilde. That's my notation for the blow up, and that's common notation. And E is common for the exceptional divisor. That's just the inverse image of this point here. Okay. Suppose so we have an example here. So it could be like P2, or we could just restrict to the affine plane that contains this point. And let's suppose we have some curve inside there. Okay, C. So like this nodal cubic curve here. And then one of the things that you might want to do is you say, well, this is the divisor here. I can pull it up back up. via this projection map, okay, and see what does it look like above. So what's happened here when you look above? Well, the inverse image of this will be corresponding to this blown nodal curve. You've got something which sits above it like this, okay, and away from this L, of course, that's all you'll have, okay. Away from that L, it corresponds to the inverse image of that. But of this L, you'll have this exceptional divisor, which is this P1. And then, so you could have a number of copies of P1, okay? So in general, that's what's going to happen, okay? So if you look at P upper star of C, you can pull back this divisor, and what do you get? You'll get something which looks like C. It's, we'll call it C tilde, which is called the strict transform. It's an irreducible curve, and we started with an irreducible curve C downstairs. And then you'll get some number of the exceptional divisor, okay? And that number is called the multiplicity of X at C. I'll tell you what that is. The other thing that's interesting to see is that this multiplicity, one way to think about it, is that it's the intersection number of C tilde with this exceptional curve E. So here I claim that when you pull back this nodal cubic curve, okay, see here you can see the 2 points where it intersects, okay, 2 points where it intersects, okay, and they intersect with multiplicity 1, as it turns out, and then so actually the multiplicity of this curve here at this point is going to be 2, corresponding to those 2 points. And the multiplicity kind of corresponds to the fact that it goes through once here and goes through, as you can see, from the blow up. Okay, so that's what's going on. So let me just define for you what's going on. So what is this multiplicity? Okay, so what you can do is that this is a smooth surface, so every divisor is going to be Cartier. So it's given by a local equation, it's locally principal. So we can look at the local ring of this surface X at that point X where you blow up. Okay, what's the local equation of that F? Okay, so that's a local equation F there. Okay. And what is this multiplicity? I'm going to call it M. Okay, so what you do is you take this local equation for C there, okay, it's F, and you say, well, what's the highest power of M that it sits inside, where M is the ideal of functions, regular functions vanishing at X, Mx. Okay, so that's a maximal ideal corresponding to that closed point X. Okay, and you look at the highest one. Okay, so it's in this Gothic M to the M, but it's not in Gothic M to the n plus 1. You look at the highest one that's in there. Okay, so if F is not in this M, okay, so that means that its M is going to be 0. Okay, so if it's not in M, that means that C doesn't go through that point. Okay, so if the local equation is going to be a unit there, okay, that means it doesn't go through the point. So of course the pullback will be just this C tilde, and there won't be any copies of the exceptional. Okay, but if it goes through that point, then it's going to contain copies of that exceptional, and the question is how many, and it's given by this simple formula here. So let me just go through a simple calculation which shows you how that works, and the way we'll do that is we'll just take this example here, but we'll look at the affine version of it, and we'll look at the patch where Z equals 1. Okay, so we'll look at the Z equals 1 patch of what goes on. So here, what we'll do is take the surface, so there'll be A2 with variables X and Y, so we set Z equals 1. And then we blow up this affine plane. So of course, this you can also get by taking this setup here and just intersecting with this affine patch, okay, or you can do it separately, just directly looking at projections away from that point inside the affine plane, and you'll get the same answer. So let's blow that up, okay, and so let's just see what is the blow up. So what you do is you close up the graph. Okay, so let's go look at the graph of this. Okay, so firstly, what's the graph? Where does it sit? So you have a point inside here. There's a point inside this X first. Okay, so there's a point inside X. And then there's a point inside this P of W star thing, which was this P1. Okay, so the P1 is basically the lines through that point 0, 0. So here's Z equals 1, so you're looking at points 0, 0 in the affine plane. Okay, so you're just basically looking at the slope. Okay, and the slope is just the ratio of big X to big Y. So these are now homogeneous coordinates inside P1, which give you basically which of these lines are you looking at. Okay, which of these lines are you looking at? Okay, so how do you close this up to get you this A2? Okay, so so here you have something that's now in this product, so it's A2 cross this P1, it's three-dimensional, but the blow-up will be just the closure of something that's two-dimensional, so it'll be two-dimensional. And how do you get that two-dimensional thing? So what's the key thing? Well, when you look at the graph, which points do you hit? Okay, so you hit precisely the ones where, well, what's this xy? So if xy is not the 0, okay, what is this ratio of x to y? There's only one point that sits above it. Well, basically, this is given by the ratio of x to y. Okay, that's that line. So if this ratio, x to y, is the same as the ratio of this x to this y, one way to write it out so that you get a nice polynomial equation is you just cross multiply. So rather than writing little y and little x is equal to big Y and big X, you cross multiply and you say little x times big Y equals big X times little y. Okay. So this is something that you have, that's the blow up of A2 at that point 0, 0. Okay, so it corresponds to an affine patch of this. Okay, so this here is kind of partly projective. It's only quasi-projective because it's inside A2 cross P1. P1 being projective, A2 being affine. So what we can do is we can look at an affine patch inside there. Okay, so what we'll do is we look where this big X, that's a homogeneous coordinate, okay, is equal to 1. If the homogeneous coordinate is equal to 1, so what do we have here now? So inside this three-dimensional space, we're looking at the coordinates little x, big Y, and little y. Now little y you can write in terms of little x and big Y. Okay, so that means that actually you only have two variables, so this is actually an affine plane, A2. So the blow-up of the affine plane at the single point has a patch, which is this affine plane here. Okay. And if you set big Y equals 1, you get another patch. So that's the other patch, and that's also the plane. And that shows you why that this is actually smooth. Okay. This one here is smooth too. Okay, so let's just see exactly what this affine plane, what the coordinates are here. So the coordinates are given as follows. It's given by little x and capital Y, big Y. So little x we put in here, but what's big Y? How is it related to original variables? Well, big Y, remember little x is equal to, big X is equal to 1. So big Y is equal to little y divided by little x. So the other variable is little y divided by little x. And that's what you have. So here you have a map from here to here. And it's quite clear to see how this map works. Okay, so what you need to do is you need to look on the coordinate rings. Here you've got polynomials in x and y. And every polynomial in x and y is certainly a polynomial in x and y on x. Okay, if you don't believe me, so you've got this inclusion map of kxy into kx y on x. Okay, you have that, and that's the map that you have. So another way you can do this is how do you send a point x and y on x? Where does that get sent to? Well, what you do is that the x coordinate here is just that x, and the y coordinate is, well, how do you get y? You just multiply these two coordinates. You can make it your y. Okay, so let's just see this in action. Okay, I won't prove this proposition, but it's essentially the calculation given in this particular example here. Okay, so let's have a look at this nodal curve here. So when z equals 1, it's just y squared minus x cubed plus x squared. So f here, the local equation, is y squared minus x cubed plus x squared, and you want to think of it in the local ring where x and y are 0. Okay, so that's what you have here. So firstly, what's the definition of the multiplicity at 0, 0? Okay, so what is this maximal ideal here? The maximal ideal is generated by x and y. Okay, so certainly if you look at all the elements inside here, okay, you have no linear terms in x and y. There's no constant term. Okay, so it's inside x comma y squared. So here, maybe I'll write that down. M is equal to x, y. So inside, if you square this, this will be in there. But if you cube it, the y squared won't be there and the x squared won't be there. So it's inside, so the multiplicity here is 2. Okay? So that's the multiplicity according to the definition that we've got here. Okay, so let's now prove this proposition in this particular example. Okay, so what we're going to do is we're going to pull back this curve, which means we just pull back the corresponding local equation. So we pull back this f here. So we take this equation, and what I'm going to do is I'm going to write this y, okay? Now we pull it up to here where the coordinates are x and y on x, so we have to write them out in this way. So y squared is y on x all squared times x squared. So it's x squared times 1x all squared. Okay. X cubed is just x squared times x, so we put the minus x cubed included like that. And then this x squared here, you've got a plus 1. And if you see what happens now is, whereas before, this equation used to be an irreducible equation, so you had an irreducible curve down here. When you pull this back up, on this affine patch here, it's no longer irreducible. Okay? It factors. Okay? So there's an x squared, and then there's this thing here. Okay, so let's have a look at this. So of course, as you can imagine, the bit which looks like this f, okay, but has this change of variables, so it's now 1 x squared minus x plus 1, okay, this is irreducible, and that corresponds to the c tilde. Okay, so that's the first thing. That's the c tilde that we get, the zeros of this inside here. Okay, so let's look at this. Okay, so the other thing is, what's the x squared referring to then? Okay, so notice that the 2 here comes from the multiplicity. Okay, and x squared equals 0, so what's the x squared equals 0 mean? X equals 0 is the exceptional curve, as it turns out. Okay, if you put in where x equals 0, okay, if x equals 0 here, and you see where this maps to, remember, the x value will be at 0. And what is the y value? The y value is the y on x value times the x value, but the x is 0, so that's going to go to 0. So that's why x equals 0. All the points where x equals 0 get sent to 0, 0, so that's the exceptional divisor. Okay, so x equals 0, that's the multiplicity, and you can see that's 2, just like what's given here. Okay, so that's why you have that here. So what about this bit here? Okay, what's the multiplicity of, what's c tilde dot e? Okay, so you want to see the 2 points and how that multiplicity works. Well, here, what you want to do is you want to intersect the c tilde, which is given by this equation, with e, which is given by x equals 0. So x equals 0, and then if you put x equals 0, and you look at this equation, okay, inside here, basically you're saying 1x squared plus 1 equals 0. Since we're working algebraically closed, you get 2 distinct roots of y and x being the 2 different square roots of minus 1. Okay, and so that's why you get 2 points, and they're each multiplicity 1. And so that's why here c tilde dot e is equal to the multiplicity of c at x. Okay, so I hope this little example kind of gives you a bit of sense of where this comes from. And really, if you just do this out in general, carry out this calculation in general, you will see this proposition. Okay, so I want to now tell you about the intersection theory of the blow-up. I've told you a little bit about what goes on with the intersection theory. And now I want to complete the picture, okay? So what we've seen, and this is the key fact, remember, is that when you blow up a surface, a smooth surface, okay, what will happen? So away from the point that you blow up, okay, it's going to be an isomorphism, okay? So it's very close to the original space. But at that point, you're going to replace that point with a P1, okay? So that's what you'll get. You'll replace it with some P1, and so they look a lot alike. And so you may think, well, tell me more about the relationship between the geometry of the two. Okay, so the first thing you might want to do is tell me about all the curves on the blob, okay, and in particular Picard groups. The Picard group of the blob x tilde, okay, so if you use the notation above, let's suppose you can do intersection theory, so your x is projected. It's just, firstly, the Picard group of x direct sum with z times this exceptional curve. So that's the first thing. So now we know what pic of x tilde is. Remember the other thing that you can do that tells you about the geometry of the surface, especially a smooth surface, is you can do intersection theory. So there's a bilinear pairing, symmetric bilinear pairing on this pic x tilde. Okay, so how is it related to this intersection theory down on x? Okay, so we've got an extra curve, so you need to throw that in too. Okay, so let's start with d and d prime inside pic x. So remember, everything inside here is either inside here or in here. Okay, so maybe the better way to write this down, if you want to write this down properly, I'll do that, is it's really, how do I get from here to here? I can do P upper star. So P is going to be the projection. And that's going to be an isomorphism, this P upper star of pic x. It will embed pic x into pic x tilde, that's P upper star. Okay? So that's the embedding that you have. P upper star, that's going to be the embedding from here to here. And then you have, well, that won't get you everything, but the point is that it has a complement, which is z times e. So everything you can write as a direct sum, or as a sum of p upper star of something inside pic x with some number of copies of this exceptional e. Okay, so let's see how you dot the various things together. So suppose you have two things which are in here. How do they dot together? So p upper star of d dot p upper star of d prime is just d dot d prime. So the intersection product is preserved under this p upper star map. What happens if you do p upper star d dot e? Okay, so you pull something up and you intersect it with this exceptional. Well, that's going to be 0. And the final thing that you need, so you know how to dot something of here with something in here, the intersection of something like that. Two things inside here. What about two things in here? You just need to know what's e squared. And the really interesting thing here is that e squared is equal to -1. So this is an example of something where the self-intersection number is negative. So you can't have negative numbers when you intersect. Okay. So let me just finish up by briefly explaining why this is true. Okay. So one of the things that you saw here is that when you do p upper star, okay. So firstly, what are all the curves on the blob? Okay. Well, if you look at the strict transform, basically they're all the same because this is almost an isomorphism. There's basically just an extra curve, which is this exceptional curve. Okay, that's the only thing that's extra. So div x tilde is equal to div x direct sum z e. And the way you can do this div x is you can make it, by this formula here, you can make a p upper star of div x if you want. Okay, so that's true. And then the thing is that, well, how do you get to the Picard group from that? What you do is you have to go modulo the principal divisors. But remember, these are birational, so the field of rational functions on both of them are the same. So to a certain extent, the principal divisors correspond as well. So when you take the quotient of both sides by the principal divisors, so the same thing, you'll also get equality. Okay, so that's why you have this isomorphism. Okay, so let's see what happens about the intersection numbers. How can you get this? So we've got the Picard groups of the blow-up. What about the intersection theory on the blow-up? Okay, so let's suppose you start with two divisors, okay, that are downstairs, okay, and you want to see what happens in the blow-up. So you have two curves downstairs here. You intersect them, okay. Now, when you pull them back, of course, something happens, okay. So, but what you can do, remember, when you do the intersection theory, remember, it's only up to linear equivalence. So you can always replace these curves with things which don't go through the point that you blew up. And then when you blow up, of course, how they intersect and things like that, it doesn't matter at that point. So that means that for all intents and purposes, calculating this, you might as well just calculate downstairs on x. And similarly, if you have exceptional curve, okay, suppose you have a point that you blow up on the surface and you have a curve that goes through it, what you can do is you can move it away from that point, okay, as a linear combination of divisors. And then when you pull that back, none of those curves that you pull back will actually touch the exceptional curve at all, so the intersection product has to be 0. So that's why p upper star d dot e is always equal to 0. So the only thing that's left to do now, which is interesting, is to show that e squared equals -1. And the calculation for this is almost done now that we've got everything set up. So what do we do here? So what we do is, what we can do is we've got a smooth surface, so of course you can pass a curve which just cuts that through that point with multiplicity 1. Okay, you can pick a local equation, okay, such that it's kind of linear. It's in m but not in m squared, okay, and you extend that out. Okay, so you pick a curve which goes to that point with multiplicity 1. Let's call it C. That's downstairs. Okay, let's pull it back upstairs and intersect with E. Remember, when you pull back something and you dot it with E, the intersection number is 0. What is P's upper star of C? So by this proposition, it's going to be the strict transform C tilde plus some copies of the exception, and the number of copies is given by the multiplicity, and we picked this C so that it's multiplicity 1, so it's C tilde plus E. Now you dot that with E. Okay, so now this is bilinear, this dot product, so this is C tilde dot E plus E squared. But what's C tilde dot E? Now we can use this fact here that this is just a multiplicity of C at X. So this term here is just 1. So it's 1 plus E squared is equal to 0. So that means that E squared has to equal -1. It's pretty cool, huh? Okay. So this proposition here is a wonderful proposition because it tells you exactly how the intersection theory, the geometry has changed in this way. If you want to study surfaces, one way to do that is to look at the curves on it and how they intersect. Okay, so this is a generalization of Bezout's theorem. Now it becomes a theory that you study. Okay, and the key point is that, well, suppose you start with this x and you blow up. What's the change? Well, essentially you just add in one curve. So more precisely, the Picard group has changed in that you now take the direct sum of the original Picard group with the ZE. And you can also know what are all the new intersection numbers in terms of the original ones downstairs. And that's given by this formula here. I hope you enjoyed this adventure in pure mathematics.